Hello viewer, we are in the third episode of electrochemistry. Till now we have discussed about the various aspects of ionic electrochemistry, that is the conductance, specific conductance, equivalent conductance and the factor affecting conductance. And the last lecture we talked about the theories which can explain the weak electrolyte, their behavior in the solution. Moving further, we have to look for the theories which can explain the behavior of a strong electrolyte in water and other similar solvents. So, today's lecture we are going to talk about Debye-Huckel theory of a strong electrolyte, as well as one of the very important phenomena which can help you to calculate many parameter, that is transport number. First, we will start with Debye-Huckel theory of a strong electrolyte. As we understand that Ostwald dilution law, Arrhenius theory of dissociation are not sufficient to explain the behavior of a strong electrolyte. These two gentlemen like Debye and Huckel has come forward with the theory which can explain the behavior of a strong electrolyte, and they put forward the theory like that electrolyte already exists as ions even in a solid state and must be completely ionized solution at all concentration. One of the important thing that can come up is the solvent behavior. The solvent which have a different dielectric constant can be understood in a simple manner, that the solvent can act as a barrier between the two ions and do not allow the ions to attract or feel each other, and that can be clearly be seen in this table, that if the dielectric constant is very high like in water, the ions do not feel each other, do not see each other, and there will be less intermolecular forces existing between them. So, low intermolecular forces between the ions, dielectric constant has to be high. If there is a high, the dielectric constant has to be low. This is a very important concept to explain this behavior of strong electrolyte. Debye-Huckel put forward an equation which enables them to calculate the magnitude of interionic effect. The opposing factor control the state of affair in solution in electrolyte. If we try to understand that how the ions are going to behave in the solution, first we have to understand that how they attract each other, and the main difference which come in a picture is due to the formation of ion pair. Ion pair is formed because we have very strong interaction between the ions, the Coulombic interaction, which try to arrange the ions in a particular manner. We have to understand that the ions like negatively charged ions is going to be surrounded by a positively charged ion and vice versa. That is going to affect the movement of the each individual ions, as well as they have to come up with the thermal collision of the ions with the solvent and between themselves. These two factors are very important and we have to understand it. Now, looking at the equation proposed by Debye-Huckel, this equation is also known as Debye-Huckel-Onsager equation. There are the terms like this is the equivalent conductance or molar conductance. This term represents the equivalent conductance at infinite dilution, and this is the concentration, and these two terms try to account for the anomaly in the behavior of strong electrolyte as compared with the weak electrolyte. This is the dielectric constant and eta is the coefficient of viscosity of medium. These two factors are very important, and then temperature, you know that the conductance is dependent on the temperature and concentration has to be moles per liter. What these two terms trying to explain you that there is a difference between the molar conductance of a strong electrolyte at any concentration and the molar conductance of a strong electrolyte at infinite dilution, and these two factors can be accounted by these two effects, the electrophoretic effect and the asymmetric effect. The first term in the earlier equation you have seen give the measure of electrophoretic effect, and the second term try to give you the asymmetric effect, and this is the two important factor which gives you a different equivalent conductance at infinite dilution at any other concentration. First we will try to understand what these two effects are. If we look at the solvent, Solvent is going to have a totally a continuous environment where an ion is moving. The moment the ion is going forward, it is going to be in the sea of molecules of the solvent which is going in opposite direction. So, it has to pass through a medium which is going in opposite direction. So, it is like a swimming in a upward flow of the water. So, it is very difficult. Same thing is felt by the ions because they have to go opposite to the flow of water, and the asymmetric effect is basically you can say that there is a ions, cations are surrounded by an ion. The moment you put a potential energy, you put a potential difference, the ion has to move, but ion the cation will move toward the cathode, anion will move to anode, but the problem is that they try to drag each other, and that is going to bring about asymmetric behavior, and this asymmetric behavior brings about the less mobility in the ions. If we try to simplify the equation that we have seen, we are trying to put the two electrophoretic effect and the asymmetric effect by two simple symbols A and B, and so that it equation become very simpler in nature and we can plot it. If we know the equivalent conductance of an strong electrolyte, we can plot it versus the square root C. The moment we do it, we should get a straight line because this is y equal to mx plus c, and the intercept should provide us with the value of equivalent conductance at infinite dilution. For water, these values can be easily be determined, and we can put these values in the equation at 25 degree Celsius, and we get the equation in this form: lambda m equal to lambda m infinity minus 60.2 plus 0.229 lambda m infinity whole term multiplied with the square root c. So, this equation become very simpler in nature and we can plot it. If you look at the forming the graph, you have plotted the molar conductance or lambda m versus square root c, and we see that behavior of strong electrolyte, they show a straight line, and the moment we extrapolate it, it touches the y axis, we are in position to get lambda m infinity from the graph, but we have to look at that the weak electrolyte cannot be used to get that. This graph says that they do not intercept at any point. So, this proves that Debye-Huckel-Onsager equation is sufficient to explain the behavior of strong electrolyte, and it follow the equation of straight line when lambda versus square root c is plotted. One of the important concept which is required to be discussed is transport number. The transport number or other name is transference number is the ratio of current carried by a given ionic species through a cross section of an electrolytic solution to the total current passing through the cross section. So, basically we are talking about the ratio of the velocity or mobility of a given ion to the sum of the velocity or mobility of the cation and anion. It is trying to give you an idea how good a ion is capable of providing or bringing out the charge from one place to another. We are aware of the Faraday's first law of electrolysis that says that number of ion discharged at an electrode is proportional to the total quantity of electricity passing through the solution. This total quantity of electricity that passes through the solution is proportional to the sum of the mobility of the ion. The quantity of electricity carried by a particular ion is proportional to the mobility of that particular ion. Definitely, it is like how faster a ion can move, the better it is able to conduct the electricity. So, if you try to put in a formula that T plus is the transport number of cation is equal to current carried by the cation divided by the total current passed through the solution, or it is equal to mobility of the cation by ratio of mobility of cation plus anion, or the transport number of an ion can be specified like current carried by the anion divided by total current passed through the solution, or it can be written in terms of mobility that U minus is the mobility of anion divided by the ratio of the mobility of cation and anion. If we try to add these two terms T plus and T minus, we are going to get 1. So, we are better placed if we have any information about the transport number of cation, we can easily find out the transport number of anion using this equation. There are basically two methods by which transport number of any cation or anion can be measured. The first method is Hittorf rule or Hittorf method. According to this rule, the loss of concentration around any electrode is proportional to the speed of the ion moving away from the electrode. The transport number of an ion is calculated from the change in concentration found experimentally around the electrode. In Hittorf method, the apparatus which is used is, it is made up of two U tubes, the two vertical glass tubes joined together through a U tube. In the middle, you can have a look at that there is a middle, there is a U tube and there are two glass apparatus which is connected through it, and each one contain a stop cork at the bottom. The U tube is also provided with a stop cork. You can have a look at these two places and the stop cork as this place as well. It is provided with stop cork or at the top of the two limbs. By closing the stop cork, the communication between the solution in the cathode and the anode limbs can be stopped. That is the purpose of putting the stop cork there. The silver anode is sealed in a glass tube and the cathode is placed in a freshly silvered foil. The apparatus is filled with a solution of silver nitrate and a steady current of about 0.01 ampere is passed for 2 to 3 hours. It is an important precaution that the current is passed only for a shorter time, so that too large a change in concentration does not take place. The apparatus is connected with a silver or copper colorimeter. There is a colorimeter here which need to use to determine how much current has passed through and how much amount of matter is deposited in that through that. When the current has been passed for about 3 hours, the stop cork at the top of the U tube are closed. The whole of the liquid in the anode compartment is carefully drained into a pre-weighted flask and its weight is determined. The silver content is determined by titrating against a standard solution of potassium thiocyanate. The weight of the silver deposited in the silver colorimeter is also noted. If a copper colorimeter used in place of silver colorimeter, the weight of the silver equivalent to the copper can be determined by using the formula 108 divided by 31.5. For the successful completion of this experiment, there should not be any change in the concentration of the solution in the U tube and we have to take care of that part. If we are using a silver electrode, in that case the nitrate ion can react with that and instead of the increase in the concentration of silver ion is observed rather than the decrease. The same experiment can also be performed by platinum electrode to avoid the attack of anion on the anode. So, basically the experiment can be done with the silver electrode as well as platinum electrode, and we need to do two different type of calculation to arrive at the result. So, when platinum electrodes are used, so they are not attacked, and after passing of current we have to do a little bit of calculation to find out the transport number. Let the weight of anodic solution taken out equal to A. We are using symbol A, grams. Weight of the silver nitrate present in it by titration is B gram. So, we can get the weight of water if we subtract this to A minus B gram. Before passing electric current, let the weight of silver nitrate in A minus B gram, you remember that we got a weight of water as A minus B gram. Before passing current, we assume that quantity as C gram. Therefore, fall in concentration is C minus B gram of silver nitrate, and to convert into equivalent weight, what has to be done? The fall in concentration has to be divided by the equivalent weight of silver nitrate and gram equivalent, and we can say that is a gram equivalent of silver, and we are going to call it by a symbol D. Let the weight of silver deposited in silver colorimeter is W1 gram and to get a equivalent weight we have to divide it by 108, and this quantity we are going to call at capital W, and we are just calling that transport number of silver ion is equal to fall in the concentration around the anode in gram equivalent, amount of silver deposited in a gram equivalent, and that is D by W. As we know that the cation and anion transport number are related, if we subtract 1 minus D by W, we are going to get the transport number of nitrate ion. Or the second case which can arise is the silver electrode is used, then we have to modify the equation. The increase in the concentration of anodic solution is equal to B minus C gram of silver nitrate, and it should be equal to B minus C divided by 170 into 108 gram of silver, or this can be written as B minus C divided by 170 gram equivalent of silver, and this quantity we are going to call as E. If no silver ion had migrated from the anode, the increase in concentration of silver ion would have been equal to W as in the earlier case. Therefore, the fall in the concentration due to migration of silver ion is W minus E. The transport number of silver ion is W minus E by W, and transport number of nitrate ion should be 1 minus this term. We will try to look at the way to calculate the transport number by solving a numerical. For example, a solution of silver nitrate containing 12.14 gram of silver in 50 ml of solution was electrolyzed between platinum electrode. After electrolysis, 50 ml of anode solution was found to contain 11.55 gram of silver, while 1.25 gram of metallic silver was deposited on the cathode. Calculate the transport number of silver ion and nitrate ion. Weight of the silver in 50 ml solution before electrolysis was 12.14 gram. Weight of silver in 50 ml of solution after electrolysis is 11.55 gram. So, fall in concentration of silver ion is 12.14 minus 11.55, which turned out to be 0.59, and when you convert into gram equivalent, the weight of silver deposited in silver colorimeter is 1.25 gram. This has to be divided by 108 and you get 0.016. The transport number of silver ion is fall in concentration around anode, the number of gram equivalent deposited in silver colorimeter. So, this term is 0.0055 divided by 0.0116, which turned out to 0.474, and as we subtract from 1, we can get the transport number of nitrate ion, that is 0.526. The second method for determination of transport number is moving boundary method. The moving boundary method is based on the direct observation of migration of ion under the influence of applied potential. This method is very accurate and has been used in recent years for precision measurement. The setup for this experiment is that it consists of long vertical tube with 2 electrodes at the 2 ends. The tube is filled with a solution of cadmium chloride. You can, it is measured here, it is shown here, the cadmium chloride at the lower end and the hydrochloric acid at the upper part of the tube. And in this way, there is a sharp boundary which exists between these two. There is a sharp boundary which is represented here due to the difference in their refractive index. The two solution has totally different refractive index. The platinum electrode are dipped in the HCl solution at the top and the anode has a cadmium stick at the bottom. On passing electric current, as there is ammeter is shown here, the passage of current through the apparatus, the hydrogen gas is evolved. There will be evolution of gas from this part, and the H plus ion are replaced by cadmium ion. The boundary line move in the upward direction. The boundary lines are moving. By moving the length through which the boundary moves and the quantity of electricity passed through the cell, the transport number of H plus can be calculated. In general, if instead of HCl we can use any other solution like AX, if the transport number of cation A plus is to be determined, the electrolyte AX solution is taken in the upper part and the layer of another electrolyte BX having a common ion X minus, as the case is shown as Cl and cadmium chloride. The common ion was chloride is introduced at the lower part. Then the electrolyte Bx is selected so that the velocity of B plus ion is less than that of A plus ion. It is also the case that with cadmium and H plus, the cadmium is less mobile as compared with the H plus ion. So, the choice of electrolyte which is filled in the lower part of the tube has to be looked at. How to do the calculation of transport number in this method? Let C be the original concentration of A plus in gram equivalent per ml of the solution. If the distance through which the boundary move, that is L centimeter, and the area of cross section is S square centimeter, the number of equivalent of A plus moving upward is the area into length into concentration, and we have to find out the Faraday of current passed, that has to be determined through the coulometer. The number of Faraday of current passed we are going to represent it by small n. The fraction of current carried by A plus ion will be n into T A plus, that is transport number of the cation. These two terms need to be equal, and when we rearrange the term, we are going to get the transport number of cation, that is T A plus, should be equal to area into length into concentration divided by number of Faraday current passed, and this n should be equal to the charge by the F is the Faraday constant. Try to look at the numerical which uses this moving boundary method. We can have a KCl 0.100 normal KCl and 0.06 normal lithium chloride. We can easily see the cation is K plus and lithium plus, and the anion are same, that is chloride. As an indicator solution, a constant current of 0.005893 ampere was passed for 2130 seconds. The boundary was observed to move through 5.6 centimeter in a tube of area 0.144 square centimeter. Then the job is to calculate the K plus and Cl minus ion transport number. Area is 0.1142 square centimeter and length is 5.6 centimeter. Q, the charge can be determined as the current into the time. The C, the concentration in gram equivalent, and this is the Faraday F 965 coulomb. The equation which we have seen earlier is S equal to multiply with L into F into C divided by Q. This is the transport number of cation, and when we put the values 0.1142 into 5.6 into 96500 into 0.1 divided by 1000 into 0.005893 into 2130, this calculation give you a value of 0.492. This is a transport number of the cation. We can get the transport number of anion if we subtract this value from 1, and that turned out to be 0.508. We are going to complete this episode, and in this we have discussed about the Debye-Heckel theory of strong electrolyte, which can explain the behavior of strong electrolyte when they are in a water or any other solvent, and we try to look at very important property, that is transport number and its method of determination. In the next episode, we are going to look at the probable application of conductometric measurement, basically conductometric titration, how to use the conductance for determination of dissociation constant, degree of dissociation and solvatory product. These are the few important application of conductometric measurement.